There's another kind of interference that you're probably familiar with, or at least you've seen, called thin film interference. If you've wondered why soap bubbles have all the different colors that they have, or why the oily spots on the road have little rainbows in them, that's what this is about. It's called thin film interference. So first, let's imagine we're looking at the road right after the rain. If there's oil on the road, and the water that comes down will float, or the oil will float on the water. I'm sorry. So the incident sunlight we're showing here is a black arrow. It goes down through the oil, then through the water, and then it would hit the road, which of course is usually pavement, and when it's wet, it's very black, so not much will come back out. Also, we're going to assume that really the light is coming straight down and going straight back out. I'm not drawing it like that so that you can see what's happening, but we're assuming you're basically looking down at your feet here. So when the light goes from the air to the oil, some of it gets reflected, we know, and some of it gets refracted. Uh, when the light goes from the oil to the water, some of it gets reflected, some of it gets refracted. I haven't drawn that ray because it then just goes down into the pavement and, like I say, pretty much gets absorbed because the pavement's so black. So let's say index of refraction of air is 1, oil is 1.2, and water is 1.33. So if we use this idea of linear superposition that we've used before when we talk about we just add up waves that come in from different sources, we can look at the light leaving the surface of the oil compared to the light that went through the oil and bounced off the water and came out. We're going to see what's the phase relationship between this black arrow and this red arrow. So first we're going to say the path length difference is just 2 times t, where t is the thickness of the oil. Now, if we were doing this more realistically and things were coming in at an angle, the way I have it drawn, we'd have to use that angle to figure out what this path difference really is. It wouldn't be straight down and back. So really we're just doing this to make life easier for ourselves. We're just saying the path difference is 2t exactly. So there's also one other rule we have to just know about this, and that is if you go from a lower value of n to a higher value of n, there's a phase shift of a half wavelength or 180 degrees or pi radians or whatever you want to call it. That does not happen if you go from high n to low n. It's only low n to high n. You can see the same thing. You might have seen this last semester if your class did waves. If you have a light, say, dental floss, very lightweight string, connected to a heavier weight string, and you snap the lightweight and send a wave down it, there will be a transmitted wave in the heavier string that goes on just like the incident wave did, but the reflected one gets turned upside down. You have a 180 degree phase shift here. On the other hand, if you snap the heavier string and send a wave down into the dental floss, both the reflected wave and the transmitted wave, there's no phase shift. So maybe this will help you remember it a little bit better. What we'd be looking at here is what's called the linear mass density of the string. So dental floss would be very low linear mass density. If you talk about the ropes that tugboats use, it'd be very high, maybe more than a kilogram per meter. Anyway, you go low to high, you get a reflection that's 180 degrees off. If you go high to low, you don't. So now we go back to our black ray that went from air to oil. We're going to get a 180 degree phase shift here because air has a lower index of refraction than oil. So there's a 180 degree shift here. Now what about the light that goes through the oil? Now it goes from 1.2 N, bounces off the water, which is 1.33. We also get a 180 degree phase shift there. So these two things that were originally in phase, we don't have to worry about the 180 degree phase shift since they both got one, and all we care about is relative phase. So we just need to know how many wavelengths fit in that extra traveled distance of 2t. The only thing we need to know now is how big is the wavelength, and this is our last complication. The wavelength in a vacuum is not the same as the wavelength in a material where n is not 1. This has to be the case because we earlier saw that lambda times f the frequency, is c, the speed of light. If this side of the equation gets divided by n because it's slowing down moving through a material, one or the other or both of these have to change. There's no way the equation can still be satisfied if we only divide one side by n. The frequency doesn't change, but the wavelength is divided by n just like c was. So what's important here is what is the path difference, this extra path, compared to a whole or half integral number of wavelengths in the oil. So a lot of times, even this kind of not great notation, you'll see lambda sub n written for the wavelength in the oil, in the stuff we care about, lambda divided by n. So we could write our equation for constructive interference in the reflected light. In other words, what light coming out of here is going to be brighter. We can write that equation as 2t equals m lambda n. This is the extra distance. This is the number of wavelength size in the oil, and this m is an integer. It's 0, 1, 2, 3, 4. It obviously can't be 0 because then we'd have no thickness. What about destructive? Well, we know half a wavelength off will destroy the interference. So 2t is equal to m plus a half times lambda n. So this tells us what would be reflected constructively, what would be reflected destructively. Different thicknesses give you different brighter colors, different constructive colors. So if the thin film is at different thicknesses all along it, which it usually is, that means different parts of it will look, say, redder or bluer, greener, whatever. That's where you're getting those colors. What about if instead of oil and water on the road, what about if we have a soap bubble? The picture's almost the same as above, but now we're going from air to soapy water back to air. Let's say N for soapy water is 1.25. We know that it's going to be greater than air, so it's not like this has to be 1.25. I'm basically just making that up. The soap bubble thickness is T, and it seems like everything is the same as the previous case, except now if this is air, soap bubble, and then air again, we do get a phase shift here, going from air to soap bubble. We do not get one here, going from soap bubble back to air. So there's a relative half wavelength shift. And what that means is these two formulas switch places, where this is what we had for constructive, this is what we have for destructive. If we have a half wavelength shift in both of them, that means now this is constructive and this is destructive. So on a test, on the formula sheet, I'm not going to be able to tell you, use this formula for constructive interference and this for destructive, because it doesn't know what the arrangement of layers will be. So this would be the case for constructive if you have oil, air, and water. This would be constructive if you have air, soap, film, air. One interesting use for this is so-called anti-reflective coatings for glasses. Because we always expect both reflected and refracted rays when there's an interface between two different values of N, people who wear glasses are used to having reflections of things behind them in their glasses, and that gets kind of annoying. You can make this a little less annoying by paying extra to get an anti-reflective coating on your glasses. So the way they do this, they take a very thin layer of something like magnesium fluoride, which is a salt, and put that on the glasses, and that makes the reflections essentially destructively interfere. So let's analyze the math here. Let's assume your glasses have an index of refraction of 1.52 and magnesium fluoride has an index of refraction of 1.38. So if we go air, magnesium fluoride, glass, we're going low, high, higher. So this is going to be just like the oil and water case. And what that means is our reflection will be destructive if the thickness matches this, m plus a half lambda n. We go for light in the center of the visible because what else would we use right now? That tells us the wavelength of this green light in magnesium fluoride is right at 400 nanometers. Now we can solve for t and say, well, our thickness is 1/2 of m plus a half, whatever that is, times 400 nanometers. There's an infinite number of solutions here. We can make m 1, 2, 3, 4. The smallest thickness will be if m equals 0. So if m equals 0, we have a half times 399, pretty much 100 nanometers. So we put a 100 nanometer thick layer of this magnesium fluoride on the lens. One thing we have to worry about, though, this is where the wavelength for destructive interference, but what about constructive interference? Where's the nearest wavelength that will be enhanced by this? Now that we know our thickness, we can plug it in here into the constructive interference formula and see, is there a value of lambda that we have to worry about here? We can do some algebra here and get 276 nanometers is m times lambda. So if m equals 1, that means light of this wavelength will actually come out brighter for us. It will constructively interfere. However, this is too short for us to see. If we used m equals 2 or 3 or 4 or any higher number, this number just gets smaller. So we don't have anything in the visible region where we'd get constructive interference from this. Now that explains why we don't use a thicker film that may be easier to work with. Who knows? We could have designed this anti-reflective coating and used m equals 100 instead. We put that into our equation to find the thickness for this. T is 1/2, 100 plus a half, 399 nanometers. Now we get about 20 microns. Our cancellation is still perfect at lambda equals 550 nanometers, so it looks like this will work just as well. However, are there places where the reflection is worse? Well, we go back like we did before and solve this. We say 2 times this thickness is m lambda over n. So m lambda equals this giant number. Now, of course, m equals 1. A wavelength this big would be in the infrared. We wouldn't have to worry about it. But all values of m are allowed. So what if we put in m of 100 here? Now it tells us we'll have constructive interference at 553 nanometers. If we put in m equals 99, it'll be 559, one at 548. So basically, with this very thick layer, we'd be getting bright, dark, bright, dark, bright, dark all through the rainbow. That's the reason we do minimum thickness for these things. Now, the last kind of interference that we're going to look at is called the Michelson-Morley interferometer. So there's a picture of this from your book. You have a laser shooting through what's sometimes called a half-silvered mirror, where half the light bounces off and half of it goes through. We've got mirrors here. Here's our beam splitter. It's also known as that. And what should happen is, if there's any change in the path length here, notice they don't have to be equal to start with. All that matters is the relative path difference. What we'll notice is a change in the interference pattern if there's any change in these arms. The reason this was set up back when people were still fighting about light being wave or a particle, one of the ideas was, we know water waves obviously require water, sound waves require air or something like that. So what is waving if light's a wave? The people back then invented this thing called the ether, and they, scientists look for it all over. They figured that's what is waving when you have a light wave. From astronomical observations, we knew the Earth couldn't be at rest with respect to the ether, so the Earth had to be moving through it. And if it's moving through it, just like, a boat moving through water, there has to be some direction light can travel where it will get speeded up by this wind that's rushing over the Earth as we move through the ether. There's got to be some place where it's faster and some place where it's slower, some direction. So when we take this beam from a laser, split it in two directions, and send them on perpendicular paths, there should be a difference in the phases of the beams when they recombine, if one of them got a shorter trip than the other. So Michelson and Morley built this thing, set it on a giant stone, and floated it in a pool of mercury. They were then able to rotate this all around and see, is there any wind, ether wind, blowing through this setup? And what they found was nothing. They couldn't see anything. So At no point was the light faster in this direction than that direction. What they would have seen is something called a fringe shift, where those light and dark bands would have moved. When they realized that they couldn't see this, they began to figure out the ether didn't really exist and light just doesn't need anything to wave in. Now, this is another one of those cases, kind of like the Hall effect, where you might think, okay, now that we've proven that, we never have to build another one of these things. But in fact, these are incredibly sensitive devices, and they've been used in a lot of experiments to measure ridiculously small changes. One of them that's been in the news a lot is LIGO, which is a gravitational wave observatory. Einstein predicted gravitational waves more than 100 years ago, and no one has ever observed them until about 10 years ago at LIGO. Because gravity is so weak, it actually detected gravitational waves from about 1 billion light years away. Length changes on the nanometer scale are easy to observe with one of these that we could build in lab. However, LIGO is set up so that it can measure changes on the scale of 1/1000th of a nanometer, which is much smaller than the size of a proton. That's what they used to discover those gravity waves.